Okay, this is lab 4. It's Wheatstone bridge. We're measuring resistance using a multimeter and the Wheatstone bridge device. The items you see around on the slide are devices we're going to be using to build the Wheatstone bridge. Okay, the Wheatstone bridge was actually invented by a gentleman named Samuel Christie. However, Charles Wheatstone in 1843 greatly improved upon it and made it popular. He, however, gave Christie full credit for it. So what is a Wheatstone bridge? Wheatstone bridge is an electrical circuit used to measure an unknown resistance. We do this by balancing two terminals of resistors in series and that are in parallel with each other. When we hook up a galvanometer in the middle of the circuit, when the galvanometer reads 0, the two terminals are equal. In other words, the voltage at D is equal to the voltage at B, and no current can flow. From there, in that balanced condition, we can calculate the unknown resistance. Here's the diagram again. We can see that current splits at A going towards terminal D and B. When the galvanometer reads 0, the circuit is balanced. In the balanced condition, we know that R2 over R1 is equal to the unknown resistance over R3 because no current is flowing, so the voltage is the same. If the bridge is unbalanced when the unknown resistor is inserted, the direction of the current tells us that R2 is too high or too low. We can adjust R2 until it balances with the unknown resistor, and in that condition, Rx is equal to R3 times the quantity R2 over R1. Now, what we're going to be using in the lab is a slide wire in which we place the two of the resistors with the wire. And that's acceptable because if you remember, the geometry is the resistance is the resistivity times the length over the cross-sectional area. The wire is the same, so the resistivity factors out in the ratio, and the cross-sectional area is the same, so it factors out. So all we'll be doing is balancing one length against another length, which makes the calculation physically easier to do. However, under that condition, we just dial in an R2 value and adjust the length instead of adjusting the resistors. This is some of the equipment we're using. This is the slide wire below. It has a steel rod that has 3 connectors on it, so we can space our instrumentation, and it has a meter stick with a heavy-duty wire in between, very carefully bolted in place. You have a resistor box, a galvanometer, a multimeter, 2 sets of spools, and a power supply that is not shown. Again, you see the configuration that we have. So in this case, we go through the same sort of math as before, and R1 would equal R2 times the quantity length 3 over length 4. This video on the right tells you how to set up and measure your multimeter correctly. If you have extraordinarily long wires, you need to measure to see if there's some resistance in them, then you'll have to subtract that out before you record. I wanted to show you before you move on what the circuits look like. So please watch this video, and if it advances too quickly, stop it, come back, look at it, and then move on. I think you'll find they'll be very useful in understanding what the data is and how it looks. Thank you. This is an example of what the spools actually are. Spool 1 is copper 22 10 meters. Spool 2 is copper 28 10 meters. Spool 3 is copper 22 20 meters. Spool 4 is copper 20 meters. Spool 4 is copper 28 20 meters. Spool 5 is copper nickel 22. And so if we connect post 2 to post 3, we basically skip over spool 2 because we have a tiny wire with low resistance in parallel to the spool, which effectively zeroes it out. So in that way we can go to 30 meters on an individual board. If we have two boards, we could go up to 60 meters if we so chose. Okay, this slide is basically dedicated to see how to connect the boards properly. So in the first case, you see that we come in from the multimeter into the first post. We then skip post 2 to 3 by tying a wire between the two, and then the multimeter connects at post 4. In this way, we only have spool 1 and spool 3 in series, so that's 30 meters of copper 22. Then if we want copper 2240, we would need a second board. So we would then take what we did before and extend post 4 to post 1 on the second board, and post 2 would then be connected to the multimeter. We could then look at another arrangement to get 50 by hooking spool 2 to spool 3 and putting the multimeter to post 4. Below you see how to connect spool 4 and spool 5 in series. Since they're wound together at the in-between post, all we'd have to do is put one end of the multimeter on the 4th post and the other multimeter on the 6th post. If we want to hook in parallel, we'd hook the multimeter up to post 5 and 6, and we connect a wire between post 4 and 6. That's effectively putting spool 4 and 5 in parallel. This is the data we would be taking with the multimeter. That also includes something not shown, which is spool 5, which was measured as 19.3 ohms. Now, we would also want to put them in series and in parallel, and we do that. We get the readings below as expected. In series, resistance adds because we increase the length. In parallel, area adds, so we decrease the resistance. This is the instructions for series and parallel. Before moving on, please watch both videos as they will tell you how the ballistic galvanometer was set up in the circuit to build a Wheatstone bridge, and it'll show you deflections. Thank you. Then we set up the slide wire value as shown in the figure. What we want to do is proceed from the power supply that's positive over to the 0 on the slide wire. From the 0 position, we want to connect our spools, one to the 0 position and one to the steel rod at the similar location. That makes the spools R1s, which are our unknowns. The other red wire goes from the 100 centimeter mark to the negative on the power supply. The decade box is connected to the other end of the steel rod and the 100 centimeter post as well. So we have two wires at the 100 meters post. In between post, we hook up our galvanometer, and that should be to the positive side. We then put the other wire, and we're going to touch the wire until we read 0 on our galvanometer. The decade box would be calibrated from 11 to 19, and then we'd zero out the 10 for most of our readings, because we want to stay as close to the center as possible. So here is our calibration circuit. Before we do this, we want to probably put our multimeter to the decade box to see if it dials in properly, because if it doesn't do it to the multimeter, it certainly will not work in the Wheatstone bridge. And as you can see here, all the numbers are consistent with each other, and in this particular data set, they're consistent with the multimeter reading. This may or may not be true in the data you have in the Excel shell. So we repeat the process of going through all the spools again once we've done the calibration, and the data is posted. What did we dial in for R2? What was length 3 measured? Can we apply the equation that you see on the right to get a value for the calculated resistance? How does it compare to the measured resistance from the multimeter? We can also do it for copper 22. We can do it for the series arrangement and the parallel arrangement. So in terms of series and parallel, we have 3 comparisons: the calculated value, the measured value, and the theory from the individual measured values. How do they compare with each other? If they're close, we've done a good job. If they're not, we either have to look for bad technique on our part or lousy equipment. This is a blow-up of the graph that you'll be doing in terms of the total length of the spool or the equivalent spool against the ohm meter reading against the calculated value for copper 22 and for copper 28. And in this particular case, we see good agreement. That may or may not be true